In this video, I'm going to cover the Birch reduction. So the Birch reduction reduces a benzene to a cyclohexadiene. So I start off with benzene. I react it with sodium metal, methanol, and ammonia, and I get cyclohexadiene. So I've taken away the aromaticity. So now I'm going to go through the step-by-step mechanism of this to show you how this reaction happens. Okay, the first step of the mechanism is the most complicated. So I have here my benzene. I'll draw in the hydrogens because some of them are going to be part of the reaction. Right? That way we have them drawn. So my first step is reaction with sodium metal, which is a radical. So I'm going to put the arrows here in a different color to make them a bit easier to see. Okay, so my one electron from the sodium will come over there. I'm going to split the double bond here with one electron going up top and one down to here. And the double bond down here will also split. So one electron there and one electron down there. So what I've gotten now is a radical anion. It's called a radical anion because I have both a lone pair of electrons up top here, right? One from the sodium, one from the double bond. I still have my double bond right there. I formed a new double bond across from the other double bond. And then I have a radical down here. That resulted from the splitting of that double bond. Okay, next step is just a simple SN2 acid, I mean, you can think about it as acid-base reaction. Right, I have my methanol. The lone pair here just goes and deprotonates the methanol. So now I've got two hydrogens up there. Still have my radical down at the bottom. So next step is another free radical, but much simpler than the first one. All that's going to happen is the sodium is going to come into here, and now I'm going to get an anion. So instead of a radical, I have the anion. The last step will be the same as step 2. My lone pair will deprotonate methanol. And I will end up with my final product, cyclohexadiene. Notice how I draw the arrows though. When it's a radical, I have to use the fishhook. So steps 1 and 3. When it's a 2-electron reaction, so steps 2 and 4, I'm using the full arrow. So make sure you use the correct arrows when you're drawing these mechanisms. Now this reaction is important because a non-conjugated diene is going to be more reactive than benzene or other aromatic compounds were. Right? This compound here will undergo, addition across the double bond of bromide or hydrohalogenation, right? It'll undergo those reactions that a benzene would not. Now, if you have substituents on the benzene ring, that's going to determine the regioselectivity of the compound. So if I have a compound with an electron donating group, so say an ethyl group, right? Alkyl groups are electron donating. They can donate some electron density into the ring. If I react to this with the same reactants, right, methanol, sodium, and ammonia, my regioselectivity will be this. I'm not reducing the carbon adjacent to the electron donating group. That's because it's not going to be stable for me to form a radical anion. So to form an anion on a carbon adjacent to an electron donating group, because I'm going to have too much electron density then. However, if I have an electron withdrawing group, so now, say like NO2, an electron withdrawing group. If I react to this with sodium, methanol, and ammonia in the Birch reduction, I will reduce at that position. So now my compound would look like this. Now notice in both of these cases that the two carbons that are reduced here in orange are across from each other. So the reduced sp3 carbons will always be across from each other in the Birch reduction, whether you have no substituents, electron donating groups, or electron withdrawing groups. So just keep in mind when you're doing this reaction what type of substituent you have, so you know where the regioselectivity of this reaction will happen.